In this little video, I'm going to introduce you to how we represent geometry. We have a different way of representing geometry than most people do. So let's start with how people usually represent geometry in the computer. So here we have what's called a line drawing or wireframe drawing of this cube. And what it makes apparent is the corners of the cube are points. So these corners are 3D points, so they have an X, Y, and Z coordinate, and there's 8 corners, and that's actually all the geometric information that's used to specify the cube. But you need to take it one step further than just having 8 points, because you don't know how they're connect up together to create an object. So you have to do additional data structures to specify the topology. And in particular, you would need to specify that this vertex is connected to this vertex to create an edge. And that these 4 edges connect together to create a polygon that serves as one of the faces of the cube. And then you need to specify you have 6 faces that together form a closed surface. So that's the usual way. It's a topological approach, sometimes called a boundary representation, because you're explicitly representing the boundary. And as I said, you just need the vertices to have the geometric information. An alternative, which is what we do, which will take a little bit to explain, is to, instead of representing the boundary, is to represent the space. And to use a different approach where we divide the space up using planes, and in this case we're using 6 planes, 1 plane for each of the 6 faces of the cube. So every polygon defines a plane, 6 faces, we get 6 planes. So over on the right, we have a binary tree where you have to use your imagination here, but at the internal nodes, each one of those corresponds to one of the 6 planes. The leaf nodes off to the right doesn't have anything drawn there. That corresponds to being outside the object. And then this one leaf node down at the far left that's marked red corresponds to the interior of the object. All right, let me see if I can try and help you understand what it is how this works. It's a little tricky because you can't really draw planes. They're infinite objects, and if you draw a lot of planes, it's really hard to tell what's going on. But computationally, there's a lot of advantages to having this representation. In particular, you can represent extremely large virtual environments and do very fast searching in them to find out what's perceptible. That's the main use of this structure. However, before we get to that, let's finish trying to understand how this might work. So, if you watch the little cube, all of a sudden there's some extra lines being drawn on it, and what's happening there is this rightmost face of the big cube, its plane is being used to split the small cube into 2, we'll call them half cubes. Now, that plane isn't moving, only the small cube is moving, so it kind of stays still. It looks like it's moving a little bit, but it's not really. And if you look over on the right side to the binary tree, you'll now see that you have 5 nodes here, and of where we used to have the entire cube, which was 6. And now over in another part of the tree, we have another 5 nodes corresponding to the other half of the cube. If we keep moving, then the small cube actually lies completely between the planes of the rightmost face and the leftmost face. So if you think of those planes going off to infinity, the small cube now lies in between them. So over here, the top node was the rightmost face, the next one's the leftmost face, and and this is was a leaf, which is now where the small cube is. 1, 2, 3, 4, 5, 6. Okay. If we keep moving it, it'll get split again, but now by the leftmost face. Actually, it's being split a little bit more. Yeah, here we go. And now we're completely over on the far side of the left face, and so we don't see any splitting. And now you can see that the cube, the small cube, is completely in one of the leaf nodes of the big cube. So as we move it around in different positions, the small guy gets split into various pieces. And you may notice that the big cube is being turned transparent, and that's because we're able to do collision detection. So as soon as these things touch, I have it in a mode where the feedback to the user is that the object that you're colliding with is turned transparent. I can also switch it to a mode where it just bounces off, so it won't allow penetration. So that would be the more physical, realistic, but if you want to do some kinds of editing where you want to actually allow penetration and you want to be able to see what the penetration really looks like, then this supports that. So collision detection is really an intersection operation, which brings us into the world of set operations. So there's other set operations, and the next one I'll show you is subtraction. So I just subtracted that small cube from the big cube, so we got a little notch. Now, in addition to subtraction, we can also do union, which is addition. Let me change the color of this cylinder, and also let me make it transparent. And then I'll move it where it penetrates the cube. And now I will add it and make sure it's deep enough. So now it's been added to the original big cube, and because it's transparent, we can actually see the volume where it's been added. And the policy on the set operation is that the cylinder took precedence over the cube, so it acts as if it did a subtraction first and then did the addition, but really it was just one operation. And then one other example of a set operation is to do cutaways. So here I'm moving a cutting plane, and this allows you to move through the interior of an object, or when you have something complicated like a building, you can cut away a lot of geometry that's occluding the interior. Okay, so that's the basic introduction to the concept of a BSP tree. Now I'd like to show you how we represent curved surfaces. So as with most graphics, we turn curved surfaces into a piecewise linear object, in other words, a polyhedron. And with a cylinder, you could just easily sample points along the endpoints, the end caps, and just use that. But that's not a very intelligent way to represent a cylinder, because a cylinder could require an unlimited number of polygons depending upon what degree of approximation you want. So instead, we intelligently build the tree using a Bezier recursive subdivision scheme so that we create a sequence of approximations. So here we're looking first at the interior, how we represent the interior, then we'll look at the exterior here in a second. So the first approximation is this square, which is, of course, is part of a cylinder, so it's just a long, elongated cube. That's our first approximation. Then we improve the approximation on each side by adding a triangle with each one of these edges. So now we have an 8-sided, have an octagon approximation. And then we can continue doing that to infinity, actually. Just keep doing the recursive subdivision. We simultaneously do the same thing on the exteriors. It's a little harder to see what's going on there, but the first 4 planes up here create a square that is analogous for the exterior. The entire cylinder is inside this square region, just like the entire interior is inside this square region. And then we cut the corners, which is what recursive subdivision does. We cut the corners and improve the approximation of the exterior. And then we just keep doing that as far as we want. So this gives us an extremely efficient search structure for which we can then do collision detection and set operations and occlusion culling and all the other things we want to be able to do. So let me show you another example. So here we have a rational Bezier curve specifying a spherical patch. So these are quadratic Bezier, and it has a similar recursive structure as we saw with the cylinder. A little bit different, but here's your first approximation of the interior, and then you improve it, and you improve it, and then same thing's happening on the exterior. It's harder to see with the Bezier patch, quadratic patch. It's just a little visually complicated, but it's the same idea. All right, so here we have collision detection. So you have these curved objects, and detecting collision between curved objects is not trivial. And here's a nice solution to it, or a very efficient way of finding where the objects collide. And then we can do a set operation and get a nice intersection curve. And so now we've converted these curved surfaces into the same representation that we can use for any object. So this is the second part of the introduction to BSP trees, a form of geometric decision trees. In the first one, I introduced the basic concept of how BSP trees use planes to subdivide space into regions that are either inside the object or outside of the object. So it carves up space, as opposed to the standard boundary representation, which just defines a surface and doesn't really say anything explicitly about the 3D space per se. You can draw inferences from that surface about the space, but you don't have an explicit representation of the space. The other thing that's different about BSP trees, as you saw in that, is that it gives you a solid representation as opposed to just a surface representation. And with that, we were able to do set operations and support the semantics of solids. In this segment, I'm going to illustrate a different but equally important property, which is visibility. Here we are back with our little cube and our big cube, but we're going to do something, we're going to look at a different property. So the first face on the right here defines a plane that's at the root of the tree, and so to the left of that left-hand side, left subtree, that corresponds to the white cube, and to the right corresponds to the cyan cube. Now, you can use that to determine a visibility ordering between these objects. What do I mean by visibility ordering? What I mean is that, first thing, it depends upon where the viewer is with respect to the objects, but it's a simple concept. In this particular case, the cyan cube would come first in the ordering, and the white cube would come second. And a simple way to use this ordering is actually to reverse it and draw from far to near. So if you just draw the white cube and then draw the cyan cube on top of it, you'll get the correct rendering of opacity. That's called the painter's algorithm. As long as I'm on one side of the plane that separates these two objects, and that's the plane of this first face, then the ordering of cyan takes priority over the white cube will hold. But as soon as I cross that plane of that first face, so here's the plane, and we're now crossing it, the ordering switches. So now the white cube would have priority over the cyan cube. And so by testing the location of the viewer with respect to that first plane, we can order these two half spaces, or these two objects, saying which one should we draw first and which one can we draw second. Once again, it depends upon the view. Now, what we can do at one plane, we can do at all of them, because the BSP tree is a recursive data structure, which means it's the same data at every node, and you apply exactly the same algorithm. It's not the same data, same type of data at every node. The actual plane differs, but the data structure is recursive, so you just apply exactly the same algorithm at every node. So it makes it very simple. You just write what you do at an internal node and write what you do at a leaf node, and you're done. And it will work then on any tree of any size. And BSP trees can represent any piecewise linear object, which are generally called polytopes or polyhedra. Can represent a set of them with any genus, and can be non-manifold, can be semi-infinite. Doesn't matter. You can have one tree represent it all. Okay, so that's another aspect then of how this works. And then we can use that to support transparency. So in order to do transparency correctly, you must have an ordering on the faces. You can't just use a Z buffer. You must order the faces. And so since we can order all of the faces from nearest to farthest, we can simulate transparency as much as we want. So here we have two transparent objects interpenetrating. Now I'll illustrate another important, very important part of having visibility ordering, and that is the ability to use what's called occlusion culling. So with the visibility ordering, you can draw far to near, like the painter's algorithm, but then you're overdrawing stuff you've already drawn before. Or you can draw near to far, but you need some sort of mechanism to maintain a record of where you've drawn, and to be able to efficiently discover that entire objects or entire pieces of objects are occluded by closer objects. And so I have an example here. We have a cube, which I'm going to use in a second to occlude the space shuttle. And if you look down here at the bottom, you have how many faces are being drawn. So it's not a lot by today's standards. But this was one of the original space shuttle models. And it's good enough for me to illustrate my point. So here I have no occlusion culling. And so when I am looking at from this particular position, while the white cube completely occludes the space shuttle, down here we're drawing 476 faces, which means we're drawing all the faces. We're not taking advantage of occlusion. But I can turn on occlusion, and now, if you look down here, we're drawing one face. So a big difference. Yes, we're talking about small numbers here for this little illustration, but this applies for very large environments. As soon as we move to a position where the space shuttle is visible, it gets rendered. Move back to where it's completely occluded, and it's no longer there.